Thanks, Prahladh. Thanks for having me. It's been a pleasure to be here. So yeah, I'll be talking about concentration of measure phenomenon on high-dimensional expanders and talk a little bit about its applications towards hardness amplification and PCPs. This is based on joint work with my wonderful colleague, Yotam Dickstein. Some of this will be review for people who are at the school. We talked a little bit about this on the last lecture that I gave, but there should be some new material for everyone. And I do want to go over everything because there's a fair number of new people, I think, who were not at the school. So, in particular, I actually want to start by re-giving definitions of high-dimensional expanders and briefly on expanders, just to make sure everybody is on the same page. Let me also say before continuing, as always, please stop me at any point if something is confusing. I'd rather people understand what's going on and we get halfway through the talk than that we get everything. So please stop me if something is confusing. Okay, so we've already heard a lot about expanders and their applications in the last week, and even in the first two talks of this workshop. Roughly speaking, expanders are typically sparse but very robustly connected graphs that can be thought of as acting like the complete graph, as being sort of sparse models for the complete graph. We've seen their ubiquitous tool in theoretical computer science. There are many different definitions, edge, vertex, etc., that we talked about. For this talk, we'll just focus on spectral definitions of expanders and later high-dimensional expanders. We saw multiple definitions of these things. Okay, roughly, so let's say we have a graph G on n vertices. Throughout the talk, everything will just be on vertex set, numbers 1 through n for simplicity. We'll always be working with that. And it will be useful throughout, we sort of talked about this a little bit in the school, to view a graph, in particular the edge set, as really a two-dimensional distribution over n choose 2, over pairs, right? What is this distribution? I just draw a random edge, right? So if I have that graph up there and I drew the edge 2, 4, then this two-dimensional distribution would get the value 2, 4. We're just going to be looking at probabilities and expectations over things, so we'll think of these sort of as distributions. Okay, when is a graph an expander? Well, the underlying adjacency, normalized adjacency matrix of the graph is stochastic and self-adjoint, and so it has a spectral decomposition and eigenvalues between 1 corresponding to the L1's vector to -1. And we all know at this point that we call G a spectral expander if all the non-trivial eigenvalues are small. In particular, it's a one-sided spectral expander if lambda 2 is small, less than gamma, and a two-sided gamma spectral expander if lambda 2 and the smallest negative eigenvalue and absolute value is also small. Right? And the complete graph will have something like 1 over n here, so this is mimicking in some sense the spectrum of the complete graph. Okay, so expanders have been very successful, but there are also places where we have not been able to make progress using just expansion, in particular in high-dimensional problems, and I'll mention in a little bit some examples of these. But there's been a great deal of progress moving sort of beyond this by trying to push definitions and applications of expanders to higher dimensions. There are multiple ways to do this. I'm just going to focus today, like I did last week in the school, on the special case of hypergraphs, probably the simplest extension of graphs to higher dimensions. Okay, so we'll look in particular just at k-uniform hypergraphs. So we'll just think of this as a subset of n choose k. Nothing more complicated, we just have k tuples. And in the study of high-dimensional expansion, it turns out it's very useful to think of these hypergraphs, in fact, as objects that are called pure simplicial complexes, which is just the downward closure of the hypergraph. Right? There's nothing complicated here. We'll just write x as the union of x0 through xk, where xk is h, and xi is a subset of I tuples that's given by downward closure of this hypergraph. So every I set that sits inside some k set in the hypergraph will be an xi. I'll note here, as I think I did in the lectures, that the notation here differs from what you may see if you look, for instance, in the topology literature. Right? I'm using I to denote I sets. You would see I to denote I plus 1 sets if you were looking in topology, but I'm going to stick with this set notation with apologies to the mathematicians in the crowd. It's a little easier from the concentration perspective. Okay, so here's a picture, right? We take a 3-uniform hypergraph and we just throw in all the edges, vertices, and the empty set for convenience as a simplicial complex. Again, just like we viewed graphs as distributions, each level sort of xi here we can view as an I-dimensional distribution, right? Just like we view the edges in a graph as a 2-dimensional distribution. How is this generated? I'm just going to draw a random hyperedge now, right? A random k-tuple And then to generate xi, I'll randomly subsample I of its vertices. And that's going to give me a natural distribution over xi, over I tuples. It sort of captures I-wise correlations within the hypergraph. So in particular, for instance, x2 is just the base graph or an underlying graph of this hypergraph. Okay, so when should we call a hypergraph or a simplicial complex a gamma local spectral expander, a high-dimensional expander? We'll use this particular definition from the literature. I'll be a little bit quicker with this than I was during the school, where we spent like an hour and 15 minutes on it. And I'll just say where the first requirement we're going to make is that x is base graph, right? If we look back here, just ignore everything above x2. This gives us some measure of pairwise correlations in the hypergraph. We'll ask that this base graph is a spectral expander, a gamma expander. And second, we'll require additionally that this holds locally. How? Within sort of every restriction, or what's called a link of x that I'll define briefly. This is sort of like, even if I fix the value of some of the variables, I still want my underlying base graph to be expanded. Okay, so let me formalize this. So given some face s in xi and an I set in a complex, the link of s is the k minus I dimensional subcomplex that's just given by a very simple procedure. I'll take all of the faces that include s in the complex, and then I'll remove s. So pictorially, is there a question? Or, okay. Pictorially, let's say I'm looking at the link of 1. Right? I just highlight everything that includes 1. Forget the rest of the object. This is not a simplicial complex, right? Because it has 1 everywhere. So I remove 1 to get sort of its local neighborhood. And in this case, this is just the graph corresponding to K3, this particular case. So this is the link of 1. And I'll say sort of just briefly distributionally, you should really think of links as saying, let's look at my k-dimensional distribution corresponding to the hypergraph. The link just says condition on this guy containing s, and look at the marginal distribution on the rest of the variables. This is exactly the same definition, because this is sort of viewing it combinatorially, this is viewing it distributionally. And if you really should do everything in terms of weighted hypergraphs, this is the, is going to tell you what the corresponding distribution on these local objects is. Okay. Right, so sorry, I should say now the formal definition. This is usually attributed to Oppenheim, maybe two-sided case to Dinur and Coffin, but it arose out of a lot of earlier work from topology and algebra. And I won't cite all the papers now, but I think I wrote many of them down in the lectures. So X is a two-sided gamma high-dimensional expander or gamma local spectral expander if the base graph of every link is a two-sided gamma spectral expander. Okay, so that's the definition. Any questions about the definition before moving on? Okay. Hopefully that doesn't mean everybody is lost, since we had like 8 hours of lectures on this. Okay, why should you care? I mean, I gave sort of some hints at the beginning about this, that somehow expanders fail for certain types of high-dimensional problems. So, okay, first, expanders have given us an incredible suite of applications throughout TCS, and algorithms and complexity. We've talked about several explicit applications in coding theory, and they're extremely, extremely powerful objects. But they're also not one-size-fits-all. Right? We've seen sort of high-dimensional problems, or even problems where you might not necessarily think they're high-dimensional, but we saw in local testability how you might need an extra layer of sort of relations between parity checks. There are lots of problems where expansion alone doesn't seem to get us all the way to the results we want. And we see this a lot, in particular in hardness amplification and PCPs. You'll hear more about this from Natalia, I think, in like 2 talks or something like this. And just generally, they often don't do a great job capturing high-dimensional systems. This was like in the mixing results we talked about, spanning trees, the Mahalasarani conjecture sort of thing. And in the last 10 years, I mean, I say here that they're starting to fill this role, but HDX have really been massively successful in this, in generalizing results from mixing to high-dimensional systems, in quantum commutation, not spectral HDX admittedly, but variants of high-dimensional expanders, and in complexity theory, in hardness amplification and PCPs, which will sort of be the main angle that we'll look at related material to this in this talk. Okay, so why are high-dimensional expanders so powerful? I mean, there are many reasons, and I'm not at all going to claim that the rest of this talk is going to tell you, uniformly why these objects are so useful. I'm going to focus on a very particular tool set. One very useful property in the context specifically of hardness amplification, PCPs, decoding, is concentration of measure. It's not clear at all what I mean by concentration of measure on a hypergraph. To start, the people who are in the school maybe do know what I was talking about, since we spent a little bit of time on this. So what does it mean for a hypergraph or a simplicial complex to be concentrated, to satisfy a strong concentration of measure? I'm going to look at sort of the most basic setting I think you could think of in this. So let's say we have the vertices of some hypergraph here. They're not laid out in a square for any particular reason other than that it was easy to draw. We'll fix some, say an adversary comes along and picks some subset of the vertices A, say half the vertices, it doesn't really matter. I would like to know whether when I sample a random hyperedge from my complex, if it sees A in the right proportion. This is equivalent to sort of a sampling guarantee that we talked about in the school. Right, so for instance, if I sampled sort of a vertical hyperedge here, I'm getting half of the vertices in the hyperedge are in A, which is exactly, the local measure now is exactly equivalent to the global measure. So it samples A well, and a horizontal hyperedge would not, right? I'd either entirely be inside A or entirely be outside A, so I'd be far from the expectation. So I'd like to argue that for high-dimensional expanders or for certain systems, most hyperedges sort of fall into this vertical component that, not literally, but that most hyperedges see about the right fraction of A. Okay, so let's now write this a little bit more formally. I'd like to ask, what's the probability that a random hyperedge from X is epsilon far from its expectation? I'd like to upper bound this. So, let's just make this clear. It's a lot of equations here. This is just the probability that this is counting the fraction of vertices in the hyperedge that are in A. It's just the sum of the indicator of A minus its expectation is greater than epsilon, should be upper bounded by some function of epsilon and K. By the adversary, yes. I want this to be true for all sets, in fact, all bounded functions, but it's not that different. Yes, A is chosen adversarially, worst case bound over A. Thanks. Okay, somebody who is not in the school, can somebody tell me if I let X be the complete hypergraph? I take all possible K sets. Think of N as way larger than K. So essentially, I just draw independently from this picture K random vertices. Somebody tell me what is the value of beta epsilon K, roughly? What's the form of, yeah. Yes, this is Chernoff or Chernoff-Hofting, right? Technically, it's Chernoff without replacement. I guess, but this is probably the most broadly used tailbound in all of TCS. It's very basic, you learn it very early on. It's extremely useful. Right? So in some sense, this question, since we can also view hypergraphs as distributions, it's really a question about what sort of distributions satisfy Chernoff or satisfy a strong tailbound, sub-Gaussian concentration. People might see this as. Okay, so first maybe let's take a step back from high-dimensional expanders. And let's say, what do we know about this problem? Right, so Chernoff is very classical. Surely it's been studied what sort of hypergraphs, what sort of distributions satisfy a Chernoff bound. And indeed, this has been extremely heavily studied. I mean, I could have put an entire slide of conditions that we know that imply Chernoff. I'll sort of summarize these in saying that with maybe one exception of spreadness that I won't go into, these are basically all properties that can only hold for very, very dense objects. So if we're interested in constructing sparse sort of derandomizations that satisfy strong concentration, we're not going to make all that much progress from this point of view. So, okay, then there's a natural question is, does there exist a sparse hypergraph X satisfying Chernoff? Right, the complete complex has n to the k hyperedges. Can we build a complex that only has a linear number of hyperedges, but nevertheless satisfies Chernoff? Is again somebody not in the school want to take a stab at what the answer is? So these are called sampler graphs or seeded extractors. Right? These have been around for, I don't know, for 30 or 40 years. They're incredibly classical and powerful tools in theoretical computer science and complexity and cryptography. Technically, these are, I guess, degree optimal samplers. I won't go quite into the exact correspondence, but we talked about a little bit in the school that you can actually construct these essentially optimally up to the constant, which can be important, don't kill me, but basically you can just take a walk on an expander. I can take my hypergraph to be a k-length walk on an expander, and it will satisfy a derandomized Chernoff bound. And this has been a really, really useful fact in the past 20 or 30 years in derandomization various applications. So in this case, I've told you that concentration is one tool that's making HDX really powerful. So if we already had this through expanders, why should I care? Right? Why is concentration somehow more powerful on high-dimensional expanders? The reason is that it turns out that Chernoff is not the only concentration bound you should care about. Right? That many applications in complexity, in particular PCPs and hardness amplification, really require concentration against broader classes of functions. Right? We were only talking before about sets or functions that sit on the vertices of the hypergraph. It turns out that one often cares about what I'll call the class of degree I functions. They're really just bounded functions or sets that sit on the I sets of the complex. Okay, I'll write out some equivalent version of the probability statement on the next slide, but it's actually easier to just look at a picture in terms of this sort of sampler graph version that I mentioned. So how do we reinterpret our sort of K versus 1, our Chernoff inequality as a sampler? We look back at sort of this inclusion, okay, before I had this 3-layer inclusion diagram. But I looked at this bipartite graph where I have K sets of the hypergraph on the top and vertices on the bottom, and I just draw an edge. If I have K set 1, 2, 4, 6, 7, etc., I draw an edge to all the guys on the bottom that it's included in. And concentration is exactly the question of saying I have some, an adversary comes along and picks a subset of the vertices. What's the probability when I randomly pick a K-set vertex up here that its fraction of neighbors is epsilon close to the expectation of A? So what does it mean to have concentration for a degree I function? It just means I'm going to replace 1 with I here, right? An adversary is going to come and pick some subcollection of I sets, and I'm going to ask what's the probability upon drawing a K-set that the fraction of its sub-I sets, which are its neighbors in this inclusion graph, is close to the expectation. Any questions about the definition here? Sorry, say again. Oh, like should I think of fixed I and then K goes to infinity? So we'll give a bound that depends on the ratio of K and I. So I guess you have some flexibility, but you should think of K as, in fact, I'll talk extensively about this actually, the relationship between K and I. This turns out to be very important. Yeah, good question. So, okay, we should probably go back and look at the complete complex, because even there it's not necessarily so obvious what the answer to this question is. So what's known for the complete complex? I'll often call this sort of inclusion sampling, but it's the same concentration question. If you go back in the literature, I'm sure you can find sort of the results in concentration of measure that you could apply to this system. They're very broad results. But as far as I know, this was first studied explicitly by Impaiazzo, Cabinets, and Wigderson in the construction of combinatorial low soundness PCPs in hardness amplification. And they proved the following bound. They said, for any bounded function sitting on I sets of the complete complex, then the concentration should be something like e to the minus epsilon squared K over I. So you lose a little bit as I increases. And indeed, as we'll talk about later, if I is like theta K, you really get nothing here. But if I is constant or root K or something, you still get very, very strong concentration. And this did give some nice constructions of PCPs, but it's a little bit limited in application for exactly the reason that you think. Right? The number of hyperedges in X is massive. X is a very dense complex. In fact, it's the most dense complex. Right? It has every possible hyperedge, so it has size n to the K. And this stops you from, for instance, building subconstant soundness PCPs of polynomial size. Okay, so IKW knew this, and they also actually proved a de-randomized version of this type of degree I concentration on what's called the Grossman, which sort of replaces sets with vector spaces. I'm not going to go deeply into it, but they managed to prove some type of Chebyshev style tail, like a 1 over polynomial bound instead of a Chernoff style, exponentially decaying bound in K. And this was great. It was shown in follow-up work of Dinur and Mayer that you could actually use this to get subconstant soundness PCPs. It's a beautiful argument that might show up in Metalli's talk because it sort of inspired the later HDX version of this. Roughly, the Grossman is polynomial size. It's not linear, but you can still get this type of concentration, which we didn't really know how to do any other way. Unfortunately, this is still limited in application due to this polynomial tail. In particular, I won't go into the details, but in this first version, you get sort of good alphabet size, but the size of your graph blows way up. In this version, the size of your hypergraph remains good, but due to this inverse polynomial tail, the alphabet that you work over gets massively, it gets exponentially blown up. So either way, you sort of lose due to either having the Chebyshev-style tail or having the very, very dense complex. Okay, this raises a natural question. Can we achieve the best of both worlds? Right? Can we get a sparse, maybe even bounded degree, right? A linear number of hyperedges complex, satisfying Chernoff or sub-Gaussian concentration? Okay, so this sort of naturally brings us back to the study of high-dimensional expanders, which, as we talked about at length in the summer school, should be viewed sort of as very strong derandomizations of products or the complete hypergraph. So we'd hope that if something satisfied this type of bound, it would be spectral high-dimensional expanders. Okay, and indeed, it turns out that, at least in sort of the Dinur-Kaufman line, this was a critical motivation in the introduction of modern spectral high-dimensional. In particular, Dinur and Kaufman proved the following result. If X is sort of a sufficiently nice high-dimensional expander, I'm going to be, sweep things under the rug a little bit and say nice enough for much of the talk, and then I'll actually say something pretty explicit about what I mean by this in a minute. But they proved that, indeed for any levels I and k in any bounded function, you get this Chebyshev-style tail bound. You get about I over epsilon squared k, which improves a little bit on what you get in the Grossman and improves significantly in degree. These are bounded degree or a linear number of hyperedge systems that satisfy this type of concentration. And I won't go into it too deeply, but this has been an extremely influential result. This is used all over the place in applications of spectral high-dimensional expansion. It's critical in these, the new breakthroughs in quasi-linear PCPs and all of the agreement testing works that come before it. It wasn't used exactly in these the original LTC papers, but it is used in some related material and some later follow-up works as well. So it's a very, very powerful guarantee that's used in the application of HDX, and hopefully, time willing, I'll talk a little bit about how it's actually used in agreement testing. In the school, we basically saw this. I'll show sort of a different version. Okay, but clearly, this is hopefully not the right answer. This is still an exponential gap from what we hoped of Chernoff type concentration. So our HDX optimal samplers, people who were here last week already know the answer is yes. You can pretty much losslessly improve this theorem. This is work with Yotam to replace whatever it was, I over k epsilon squared with the correct e to the minus epsilon squared k over I. I'm ignoring constants everywhere, by the way. So there's probably some large constant in the exponent, or small constant, I guess, 0.001 or something in the exponent here. And also, I didn't mention this before, but this is tight. You can also show by sort of reduction to tightness of Chernoff that no inclusion sampler, no sort of degree I concentration can be better than e to the minus epsilon squared k over I. So this is sort of the right answer. Sorry? How big is X? X for every vertex, the best construction of this, which comes from the Ramanujan complexes, each X will sit in about 2 to the d choose 2 hyperedges. The number of vertices times 2 to the d choose 2. So this I'm going to touch on this a little bit at the end, although maybe not given time constraints. But this is a very interesting question because expander walks would get you just linear dependent. It would get you 2 to the d or 10 to the d or something like this. And here we're losing, we're getting 10 to the d squared. We're paying somehow for this stronger concentration. It's not clear this is necessary. I think it's an extremely interesting question that I'll touch on in a bit. I want to say a disclaimer here. I've been motivating all of these results in the context of PCPs, and they are really a critical component in these arguments, but they're certainly not the only components. This alone does not lead to better PCPs. You need both an improved agreement test, which we talked about a bit last week, and if I have time, I'll cover. And you also need a better embedding theorem, which I won't talk about, but I am guessing will be covered in Vitaly's talk. Yeah. I'm going to very explicitly say this. I'll make sure that we cover it. But yeah, for now, let me rush it under the rug. Okay, so now I want to come back to the question that was asked earlier. How should we think of the relation between I and k? Particularly, I want to look at this regime where I is like k over 2 is theta of k. And here the bound that we've given, because there's probably like 0.001 or something in the constant there, is basically trivial. What this will really work out to is that it's saying this probability is less than or equal to 1, which is not a super useful bound, it turns out. So unfortunately, it also turns out this is an extremely important regime. Like if you want to build PCPs with optimal soundness, you actually really need to be taking I in this type of concentration to be theta k. So is there anything that we can do in this setting? Okay, like I mentioned, this actually was an issue in this original paper of Impaiazzo, Kavanitz, and Vigderson. Their PCPs were not optimal because they had to set I to be root k in order to get this concentration to be non-trivial to work. So is there anything we can do about this? Can we give some relaxed notion of concentration or something like this when I is theta k? And the answer is yes, but we need to take a little bit of a slight detour from what we've been talking about here into one of the main topics from last week, the down-up walk on a complex. So I'll be fairly brief about this. The k/2 step down-up walk on a complex from a random starting point is the following basic procedure. I'm going to pick an S uniformly at random, a random hyperedge in my complex. I'm going to subsample half of its vertices. So in this diagram, I'm going to move from S down to T. And then I'm going to supersample an S prime that contains T. This is called the down-up walk. We went over it extremely extensively last week. Has nice mixing properties, et cetera, et cetera. So it turns out that this studying this will sort of be the answer to this I equals theta k case. In particular, the idea, which is due to Dinur and Livni-Nevan, is a really beautiful idea, is to replace sampling with what's called reverse hypercontractivity. Analytic, or maybe some people call it a small set mixing type inequality. It's really a statement about connectivity in the down-up walk. It says the following. It says, take any subsets A and B of the hyperedges. So take some collections of hyperedges that have at least noticeable measure, that have measure more than like 2 to the minus k. The probability across these pairs SS prime drawn from the down-up walk that I move between A and B, the first guy lands in A, right, and the second guy lands in B, should be at least some polynomial in their measure, the product of their measure. And so if there was sort of no correlation here, right, if I just drew S and S prime completely independently, the probability of passing between them would be measure of A times measure of B. So here we're saying you can't quite achieve measure of A times measure of B, but you can get sort of surprisingly close. You can get within a polynomial factor. I'll say briefly, why is this called reverse hypercontractivity? Because if I flipped this inequality sign here and changed the polynomials, this would be what's called two-function hypercontractivity in standard Boolean analysis. So it is sort of a reverse of hypercontractivity. But I won't go too much into this. Any questions on this guarantee, actually? Yeah.
Does the polynomial, the constant and exponent depend on k?
No. It's critical that it does not depend on. It's an absolute constant. And in fact, I picked the k/2 down-up walk. The constant depends on if I were to go to 3k/4 or gamma times k, it would depend on that value. You should think of this as like the noise parameter. So if I had more time, I would have done this for the noise operator, but I didn't want to go into defining the noise operator and this sort of thing. So yeah, think of it as, I don't know, 100, or it's some absolute constant in this case. Yeah, good question. It should not depend on k. It's not a very useful result. Should be like a half, right? I'm replacing each guy with, yes, yeah, exactly. It's like a noise operator with probably a half. Yeah, the only difference really is in the noise operator. Actually, there is an interesting difference, which is like, why did I have to require this non-trivial, it's back. Why did I require this non-trivial measure? And if we had the noise operator, I wouldn't have to require this because there's a 2 to the minus k probability that I just resample everything. Here, I always have this intersection, so it's really easy to actually construct counterexamples of sets of size about 2 to the minus k where I'll never move between. So yeah, there's some differences in moving between noise and down up, but it's roughly the same up to this. This is essentially tight up to the polynomial and the exponent. Okay, so what does this have to do with concentration? Hopefully it's already a little bit clear from this diagram. I want to rephrase a little bit how I draw the down-up walk. Right? Before I was saying I start at S, I move down to T, and then I move back up to S prime. But I could equivalently draw this pair by first sampling a random k/2 set T, and then independently sampling S and S prime given T. So what does this say? The probability that I land in A and B is basically exactly saying that maybe not many T, but a non-trivial fraction of T corresponding to the measure of A and B, have to see a reasonable fraction of A and B, right? When I fix T, what's the probability that I land in A and land in B? It's just the product of the local measure of A and B as seen from T. And so this is a sampling type of question. It's just that the parameters are now sort of depend multiplicatively or polynomially on the measure of A and B. So it's a little bit of a different regime, but it's still very much a sampling or concentration style flavor result. Okay, any other questions before moving on? Okay, so let's ask the same question as we asked before. What hypergraph families satisfy reverse hypercontractivity? So originally this property was proved by Borel for the hypercube, or maybe from Gaussian space. And it was sort of reintroduced within TCS by a list of people I now can't remember, Mosul, Boschkubitz, Regev, Steif, and Sudakov, I think. It was later proved by Mosul, Boschkubitz, and Sen that this can be generalized to product spaces and more generally to spaces with some type of nice entropy contraction behavior, something called a modified log Sobolev inequality. I'm not going to deeply go into that. For people who were here last week, if you remember this sort of down-up walk mixing that I covered, and I mentioned at the end that we could replace variance with entropy, that's what this is. If you had sort of nice local entropy contraction behavior, you'll get this type of bound. As far as I know, this is the only systems that reverse hypercontractivity are known for. It's an extremely restrictive property. And using it, Dinur and Weizmann were able to sort of fix these original PCPs of IKW and sort of get to optimal soundness by essentially setting I to be K over 2 and using reverse hypercontractivity instead. But we still have the same problem, right? These are great PCPs. They essentially match parallel repetition combinatorially, but they're still limited because they're still of size n to the K, right? They're still every possible hyperedge. So we'd like there to be sparse complexes satisfying this notion of reverse hypercontractivity. This seems much, much more challenging because entropy contraction, modified log Sobolev inequalities, these are very, very powerful inequalities that somehow inherently cannot hold on sparse complexes. I'm not going to go deeply into it, but MLSI, for instance, implies that sort of this random walk corresponding to the down-up walk mixes in time like log n, and on a bounded degree object, you cannot mix faster than log n. So it's not possible to have bounded modified log Sobolev or these strong functional inequalities on bounded degree complexes. This seems like a little bit of a problem. You need some sort of totally new way to prove reverse hypercontractivity to get this. Indeed, it turns out that there is sort of a fully combinatorial or probabilistic proof of reverse hypercontractivity, at least in this form that I've presented to you. That's sort of a local to global approach, like we talked about last week, which basically says that if you give me a complex X that has optimal K versus I, this e to the minus K over I sampling for all I and in all links of the complex, then X is automatically reverse hypercontractive. So if I have optimal concentration in all local parts of the complex and the global complex itself, it automatically implies reverse hypercontractivity. It's a sort of small step mixing type result. And this, of course, implies that all nice enough HDX are reverse hypercontractive, right? Because the links of HDX are HDX. So if we had concentration for the global object, but the theorem we showed before automatically implies optimal concentration for all the links as well. So we get reverse hypercontractivity on high dimensional expanders. Okay, now I think I get to the question. Yeah, now I get to the question of what is a nice enough high dimensional expander. Well, I'll pause. Are there any questions about this before moving on? Okay, great. So let me get to Ramprasad's question about, I've been sort of brushing under the rug. What is a nice enough high dimensional expander? So this is actually something I wanted to talk about in the school, but didn't have time. High dimensional expanders exhibit a phase transition. I think an extremely interesting phenomenon at a certain spectral expansion parameter. In particular, when the top links, the codimension to fix everything but 2 variables and look at the graph, when this has expansion 1 over d, 1 over dimension, HDX exhibit a number of thresholds. The first, for instance, we talked about Oppenheim's trickling down theorem last week. This will work at any lambda 2 less than 1 over d and completely breaks at 1 over d. You can't infer spectral expansion of the one skeleton if you only start at 1 over d. You immediately get to infer some non-trivial spectral expansion as soon as you go below 1 over d. Same thing can actually be proved for these rapid mixing results. This comes from some construction of Golowich that achieves exactly 1 over d by tensoring. Yeah.
Sorry.
Ah, crap. Yeah, D is the top dimension of the complex. Sorry. Yeah, so actually there is a reason for this, which is I'm about to say something about looking at lower skeletons of a D-dimensional complex. Thank you. D is dimension, it used to be K. Apologies. This comes from sort of looking at a construction of Golowicz that constructs 1 over D strength HDX by tensoring a graph and the complete complex together. And roughly the moral intuition is that this object still acts like a graph. So it doesn't have these sort of local to global phenomenon that a true strong high-dimensional expander does. It comes from these like algebraic constructions. So with this in mind, I want to call a complex sort of lambda TD, standing for trickling down, if its expansion is less than lambda over D. So if it's sort of just slightly under this barrier of 1 over D, where we know that you can't get any sort of strong local to global behavior. So we prove the following result. This is why I use D instead of K, that if you take a skeleton of any lambda TD complex, for any lambda less than 1, you will get optimal concentration. So in particular, for any K that's less than or equal to the square root D, so if I look at square root degrees down the complex, I'll recover something like 1 minus lambda, maybe it should be root 1 minus lambda, epsilon squared K over I. So this becomes trivial as lambda goes to 1. And again, this is necessary. We prove that when lambda equals 1 at this threshold, you can build constructions, namely Lewis complexes, that satisfy no non-trivial concentration at all. So this is sort of a sharp, another example of this same sharp threshold phenomenon occurring on high-dimensional expanders. Yeah. It should be 1 over D, and it's because I'm using set notation and not. It should be half. No, the links. Sorry, for 3 dimensions. Sorry, for triangles, your 1 links at half. You can't use trickling down. Oh, so maybe it is D minus 1. Ah, shoot. Okay, D minus 1. Yeah. Okay, I think it should be D minus 1. Okay, I apologize. Yeah, thank you. Yes, size. Yeah, just think triangles, 1/2. Yeah. D is always, like when I say dimension, I mean size. I'm sorry. For most of these things, it doesn't matter. For this particular one, there is like a very sharp threshold, so it does sort of matter. Sorry about that. Okay, good catch. Okay, I'll note that we actually prove, a litany of example or particular settings where you get strong concentration. So if you want concentration on the very top level of the complex instead of a skeleton, we can also get this, but only under much stronger, if we assume lambda is like exponentially small in the size dimension, in the one-sided partite or two-sided case. And really, we give some sort of bound that interpolates. You give me an expansion parameter, I give you some sort of exponential concentration bound that ranges between root K and K in the exponent. And I'll mention at the end, we don't know if this is tight. It's open to prove, for instance, full Chernoff for the top level of weak high-dimensional expanders. I don't know what the answer should be. Okay, I have about 10 minutes, maybe seven or so minutes. Okay, so I wanted to talk briefly about agreement testing. Okay, I think I'm on track. So I want to actually show you, some people in the summer or spring school already saw some variants of this, but I do want to talk a little bit about where this sort of thing comes up in the study of PCPs and hardest amplification. In particular, it comes up in this sort of combinatorial analog of PCPs, or formally some type of local testability called agreement testing. So agreement testing is some sort of core paradigm in the construction of PCPs. And it roughly follows the following setup. We'll have some universe U. For our case, that's just going to be the vertices of our complex X. We'll have some family of overlapping subsets. In this case, it's just the K-sets of our complex. And we'll be given a family of local assignments. For every K-set, we're going to get sort of a labeling of the vertices, a 0-1 labeling of the vertices that are in this K-set. And people who were here last week have seen this before. And our goal is to test whether all these local overlapping assignments really correspond to a single global function on the vertices of the complex, right? So we'd like to infer, does there exist some G, some function on the vertices here, such that f of s, locally is really just the restriction of G to that particular subset. And in the context of hardness amplification, This really corresponds to I start with sort of a weakly hard problem on the vertices, and I try to sort of amplify it by doing some type of derandomized k-wise repetition. And these local responses are basically k-wise answers to the question, and I'm trying to figure out, is it really corresponding to a solution to my original problem? This is sort of the main thing you need to solve in hardness amplification. Okay. So roughly speaking, an agreement test queries about O of 1 positions in my assignment, queries O of 1 k-sets, and we'd like it to satisfy completeness, meaning if F is truly global, then my test should pass. And the converse, soundness, if the test passes, then F should indeed be close to a global function in some way. Okay, so what do these typical tests look like? I usually just sort of query maybe 2 or 3 guys that intersect. I check their intersection, and if they agree, then I accept, right? I want to show that if sort of random pair that intersects agrees, this implies the existence of some global function. What's the best thing you could possibly hope to prove? We'll be interested in what's called the 1% regime. There's actually a different regime than we talked about last week. It's much, much more challenging. We sort of want to prove that if our test even passes with non-trivial probability, some small probability, it still implies some correlation with the global function. In particular, note that a random function will pass this test with probability about e to the minus k. Roughly, like if I look at how many intersecting guys there are and I just flip coins to assign the values, the probability I get things that agree on all the random flips, it's roughly like e to the minus k. If I query O of 1 things, I can only query O of k guys. So this is sort of the best, a random function will always pass this sort of test with this probability. So what you want to prove is that if the test passes with probability, much more than a random function, I should actually be able to infer some global structure, right? I want to be able to find some function g such that F is like omega delta correlated with g. Okay, I'm basically out of time, so I won't go into too much detail here. We study sort of 2 types of tests on high-dimensional expanders. The v-test, which is just given by the down-up walk. This is this k versus k over 2 versus k. Right? You just check agreement in their intersection. It turns out there are known lower bounds saying you can't beat soundness about 1 over k for this type of construction. So we'll also look at what's called the z-test, which is in Pagliazzo, Cabinets, and Richardson. Realize you can fix this by sort of adding a third query here. And as you can see, this is definitely a z. You just have to sort of lean back a little bit. Okay, so Dinur and Levine proved that on the complete complex, you indeed get soundness 2 to the minus k with the z-test. So we prove the following things. First, the way that you typically prove this type of agreement test is you first prove sort of a local example. This is sort of similar to these local lists of functions that Shashank had in his talk that he was trying to then patch together to get a global list. You prove that sort of given a nice enough high-dimensional spanner, like a reverse hypercontractive complex, then if the test passes with probability much bigger than 2 to the minus k, then many of the local restrictions, you can get sort of global decodings of a function on the vertices. The trick is that you now need to patch these local solutions together, sort of similar to what Shashank was talking about. Unfortunately, it turns out there are known lower bounds for this. That using only spectral expansion, this is impossible. I don't have time to explain why. Maybe Metalli will talk about it a little bit in her talk. So we'll assume something slightly stronger for this 1% testing. We'll assume that I'm going to say X is what's called global, which means if I take a random pair of k over 2 sets, T and T prime, I'm going to say that most of the time, I want their union to be a k hyperedge. Right? So if I take 2 random k over 2 guys, I want to say with high probability, their union lives in level k, the complex. Under this assumption, we show that for nice enough high-dimensional expanders that are global in this way, you indeed get an essentially optimal agreement test. This is also, I guess I'll say, because we're talking about coding, this is equivalent to some 1% regime local testability of the direct product code corresponding to the complex X. So you get optimal soundness, and while we don't have sparse examples of complexes that are global, which is what we would really want, it at least does extend known results. This sort of optimal agreement test was really only known for products in the complete complex, and you can extend this now to sufficiently dense random objects, full linear matroids, skeletons of many sort of combinatorial spin systems that are studied in the literature. So you get many, many more examples of complexes that satisfy optimal agreement tests from using this type of machinery. Okay, I'm basically out of time, so I just want to mention some open questions that I alluded to throughout the talk. The first is, can we show that weak high-dimensional expanders satisfy a true Chernoff bound at the top level? Right? I said that I can prove that if you sort of go down to a square root d skeleton, then you can get optimal concentration. But I have no idea if at the top level of the complex, the best bound is like e to the minus square root dimension or e to the minus dimension. This is open. I think it's a very natural and fundamental problem. It's also related to the last problem I'm going to say. The second question is obviously, can we weaken globalness or find some weaker condition that maintains optimal or exponentially strong soundness in an agreement test? There are agreement tests known on sparse complexes. This is how we got these incredible new PCP construction. But the best soundness is 1 over log k. So it's doubly exponentially far from what you would hope for and what we know for stronger PCPs. And of course, there are other ideas you need to try to use these to build better low soundness PCPs, improving on the one you'll hear about in two or three talks. And finally, I want to address this degree question briefly that was asked. It turns out that you can prove without too much difficulty that any maybe sufficiently regular complex X that satisfies true Chernoff in all links has to have degree 2 to the d squared, 2 to the omega d squared, and that this bound is matched by the Ramanujan complexes. That our best possible constructions of HDX have degree 2 to the O of d squared. So up to the exponent, these match. But like I said in Q1, we don't actually know if these weak high-dimensional expanders satisfy Chernoff. So the question is this tight? Does every high-dimensional expander have degree at least 2 to the d squared, or are there better constructions, say almost matching the degree of expander walks or something like this? And like I mentioned, if you resolve Q1 in the positive, it automatically resolves Q3. You automatically get 2 to the d squared bounds, and combined with the Ramanujan complexes, this would say that this is optimal. Okay, so I'll finish up there. Thanks so much. It depends what you set the field parameter to be. Right? They're over some FQ or FP. So if you set P to be like 1 over d squared, sorry, like d squared or something like that, then they will be. Right? The top length should have expansion like 1 over square root P or something. So yeah. No, so one-sided partite, basically everything I said holds under one-sided partite, or actually just, I mean, partite, it makes things easier. Like it's actually a nice, okay, and we can talk about it after. In most cases, it makes it easier.
Anybody else? Question regarding, so you had the Chernoff bound implies the reverse hypercontractivity. Do you have a statement, I think, of the converse?
No, it's a good question. I don't know. And it's really the argument has no wiggle room. You really need exactly e to the minus k over I for all I and all links to get it, or at least up to half links to get it to work. I think it's a very interesting question if you get the reverse. I think for every example that we know probably does satisfy, I mean, if you satisfy MLSI, you automatically satisfy strong concentration of measure. So there probably are not any counter examples that, so far, but it's a great question. I don't know. Nick had a question. Yeah, so this is the agreement testing is equivalent to local testability of a direct product code. Yeah, we covered this in the school last week, but this is just like, is this visible? This color or not? Okay, well, sorry. Next question. So you have like your vertices here. You have your k-sets here. I have some string, sitting along here. And my code is just, I concatenate the symbols of the string that I see. What I'm testing is exactly, am I an element in this, right? We call this the direct product code. It's, I guess, the ABN and R with no base code. Am I an element of this is exactly what I'm testing in an agreement test. Yeah, sorry, I covered that last week. That was not a helpful comment to the people who just came.